Sounds. This is lesson 3 of the sounds topic. This presentation will play automatically. You don't need to press any keys to advance it. You just need to pay attention and listen. So to start with, we're just going to ask a couple of questions to recap on last lesson. First of all, which travels faster, sound or light? Hopefully you've all chosen light, and you may remember light travels about 1 million times faster than sound, 300 million meters a second, whereas sound travels about 330 meters per second. Next, why can't sound travel through space? Well, the basic answer is there's no medium to carry the sound. You might have said there's no air, particles in space, but sound can also travel through solids and liquids. And if you remember, it's fastest through solids, then liquids, and slowest through gases. Finally, can you remember the word for a space that has no particles in it? Well, the word is a vacuum, and that's unusual because it has 2 U's next to each other. I don't know any other words that have that. Three learning objectives for this lesson. Firstly, to describe the parts of the ear and their functions. Secondly, to describe how microphones convert sounds into electrical signals. And finally, to recall that different animals have different hearing ranges. This question isn't too difficult. What organ do we use to detect sounds? Okay, we're going to have a look at the parts of the ear, the main parts that make it up. So if we start with the outside, we have the outer ear, which captures sound waves and channels them in. It also helps us to locate the direction from where the sound is coming. And the ear canal is the hole which goes towards the middle of your head. The sound waves go in there. At the end of that ear canal, there is the eardrum. This is a very thin membrane, and as sound waves come into the ear canal, it causes the eardrum to vibrate. Attached to the other side of the eardrum is the first of 3 very small bones. These are the smallest bones in the body. The first one's called the hammer. That's connected to another one called the anvil, and finally one called a stirrup. And you can see that if you know what a stirrup looks like, it's the shape of a stirrup. The stirrup then makes contact with a device called the cochlea, and this looks a bit like a coiled up snail shell. And if you look at the diagram there, you can see the kind of brown things coming off that. Those are the nerves which take the information to the brain. They're called the auditory nerve, and of course all of this is encased in the skull. Okay, I'm not going to read all these out for you, but I'd like you just to read through the 6 stages there, which is pretty much what I've just been through, to try and build up a picture of how the ear works to detect sound. So I'll leave you with that for a few seconds, and then we'll go on and we're going to watch a short video about how the ear works.
Have you ever wondered how sounds make their way from the source all the way to your brain? Take a trumpet, for instance. When it's played, it makes sound waves in the air. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves reach the eardrum, which is a membrane roughly half the size of a dime. They make the eardrum vibrate, which in turn vibrates 3 tiny bones called the malleus, incus, and stapes. These bones amplify or increase the sound vibrations and send them to the cochlea. The cochlea is shaped like a snail and is the size of a garden pea. It is filled with fluid, and the sound vibrations make this fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea ride these waves, and the hair bundles are moved. The hair bundle on top of the hair cell turns these movements into electrical signals. As the hair bundles are moved, ions rush into the top of the hair cells, causing the release of chemicals at the bottom of the hair cells. The chemicals bind to the auditory nerve cells and create an electrical signal, which travels along the auditory nerve to the brain. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect higher-pitched sounds, such as a piccolo or flute. The hair cells toward the top of the spiral detect progressively lower-pitched sounds, such as a trumpet or trombone. At the very top or apex of the spiral, the hair cells detect the lowest-pitched sounds, such as a tuba. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand.
Just a quick recap question. Can you put these parts of the ear in the correct order from the outside to the inside? So you've got 1, 2, 3, 4, 5 structures. Put them in the correct order. And you should start with ear canal, then the eardrum, the ear bones, the cochlea, and finally the auditory nerve. Just a little fun fact here that owls, I'm sure you're aware, have very good hearing. They operate as well as good vision usually. The long-haired owl looks as though it has ears, but these are not in fact ears, but they may be kind of fake ears to make it look like something different. Owls do have very good ears, but they have these channels through their feathers which allow them to locate their prey very precisely. Okay, we're going to look at a little bit at how loud sounds are. And loud sounds, I'm sure you know, can damage your ears. People who work in noisy environments such as factories or construction wear ear defenders. These can either be the type that go over the outside of the ear, which you can see at the top, or they can be earplugs at the bottom. Soft furnishings in your home, like curtains and carpets, can absorb sound, and you can buy special foam, which looks a bit like an egg box there, and that absorbs sounds and can be used to soundproof rooms, such as recording studios where they don't want any noise from outside getting in. So, how do we measure the loudness of sound? Sound is actually measured, the loudness of sound is actually measured in something called decibels, little d, big B. And every 10 decibels is actually a doubling in the intensity of that sound. So if you look at the chart on the right-hand side, a screaming baby makes a noise about 80 decibels, and compared to a normal conversation, which is 60 decibels, so that's an increase in 20 decibels. Now that's, you might think 80 is 20 more than 60, so that's only an increase of about a third, but in fact going from 60 to 70 is doubling the sound, and going from 70 to 80 is doubling it again. So 80 decibels is 4 times as loud as a normal conversation. Long periods of exposure to sounds above 80 decibels can damage your hearing. So 80 decibels there, above that we're looking at lawnmower and chainsaw. So if you have prolonged exposure to that, it can be damaging. but even short exposure to sounds above 120 decibels can permanently damage hearing. So they're the things like jet engines and gunshots. Our second objective was to look at the way microphones work, and they work in many respects in a similar way to our ears. Sound waves cause a diaphragm, which is a thin membrane, to vibrate, and that's quite similar to the way our eardrum vibrates when sounds hit that. This vibration is then converted into electric currents in the microphone, and that goes off to be processed. In a similar way, the cochlea in our ears takes the movement, the vibration, and changes it into an electric signal. So both ears and microphones convert sound energy into electrical signals. The auditory range is the range of frequencies that you can detect. And for humans, we can detect anything from about 20 hertz, that's 20 waves per second, to 20,000 hertz. Most of what we hear is in the lower part of that range. And as you get older, you tend to lose the ability to hear the high-end sounds. Sounds below 20 hertz, we can't hear those. Those are called infrasound, and sounds above 20,000 are called ultrasound. And if you look at the diagram, you can see that there's certain animals there. The bats can detect ultrasound. Elephants can detect infrasound through their feet. There's another picture here just showing the different auditory ranges of different animals. So humans at the top there, infrasound less than 20, ultrasound above 20,000. And you can see that elephants and moles can hear the low intensity, and they detect these more as vibrations through, as I said, through elephants' feet. Cats and dogs can detect a higher range than we can, and very high up the frequency range are animals such as. So just a couple of questions. If you look at the chart, a slightly different chart on the right, it shows different types of animal and their range of frequencies. So first question, which animal can hear the highest frequency sound? You should have worked out that's the dolphins down at the bottom. They can hear about 150,000 hertz. Second question, which animals can hear the lowest frequency sounds? There are a few down at the bottom end, humans, owls down at 20, but elephants actually are the one with the lowest. They can hear down to about 16. And finally, which animal can hear the greatest range of sound frequencies? Well, that's the widest bar, and again it's dolphins, who can hear from about 20 all the way up to 150,000. Okay, we're almost at the end of this lesson now. Coming up, there's just a very quick fun quiz. You're going to hear 10 animal sounds and you have to try and guess what they are. When you finish that, the next thing I'd like you to do, can you please make sure you complete at least one of the worksheets? You can choose which one, and also complete the recap quiz on forms just to reinforce everything that you've learnt in this lesson. Okay, until next time, goodbye.